Is that, let's see, there we go. Is it working?
Perfect.
And am I loud and clear?
You are.
Okay, thank you. And I had a lot of help from my co-authors, Dan Pace and Lindsay Craig, Richard Bedell, and Marilyn Miller. And like many geological exploration talks, there is some forward-looking information involved. There's a lot of risks associated with exploration, as we all know, and there's no assurance that exploration will lead to gold mining in any particular place. There's always uncertainties. But at any rate, the Silicon Project is located in the Bear Mountain Mining District, which is in southern Nye County, shown by the yellow star here, several hours by highway northwest of Las Vegas, but just a few miles northeast of Beatty and a little bit further away from Reno. It's a new, Silicon is a new volcanic hosted epithermal gold play in the southwestern Nevada volcanic field. It's characterized by a very large advanced argillic steam heated cap with alunite and kaolinite and mercury mineralization. And it was initially staked by Renaissance Gold in 2014. And then in 2017, AngloGold Ashanti signed an option earning agreement. It was originally anticipated that there would be 2 GSN 2020 Symposium papers and talks on Silicon, and one of them was going to talk about the initial reconnaissance exploration that Renaissance did to appreciate the property and stake it, and that's the subject of tonight's talk. And then another paper was going to talk about more detailed exploration and drilling results to be given by AngloGold Ashanti geologists. But unfortunately, due to circumstances beyond the control of all of the geologists involved, those drill results have not yet been made public, and consequently that second paper and talk have been delayed. And I know the AngloGold geologists are very anxious to tell their story. They have some very interesting things to say about what should prove to be a very interesting gold deposit. But meanwhile, what Anglo has released about Silicon is the fact that detailed geologic mapping has been completed, gravity, magnetic, and IP surveys have been completed, and so far at least 47 drill holes with an aggregate length of over 62,000 feet have been drilled. And just recently, they completed the last installment of $3 million in payments in order to gain 100% interest in the property with an underlying 2.5% royalty. So Nevada, in terms of gold, is most famous for its Carlin-type deposits in the northern and central parts of the state. But most of us know that Nevada is also famous for some world-class volcanic-hosted epithermal precious metal districts. Probably the most famous one would be the Comstock, located just south of Reno, produced about 8 million ounces of gold and nearly 200 million ounces of silver. Another example is the Mammoth Round Mountain gold deposit in central Nevada, whose total mineable endowment is on the order of 20 million ounces gold. And then there's Goldfield, one of the world's highest grade, high sulfidation gold system, whose more than 4 million mined ounces, much of them came at grades of 1 ounce per ton or higher. Then there's Tonopah, a little bit further to the north, 170 plus million ounces of silver, nearly 2 million ounces of gold. And then closer to Silicon, down here in the southwestern Nevada volcanic field, are the Bullfrog and Bear Mountain mining districts that have produced nearly 3 million ounces of gold, but with a lot of recent resource estimates. If we add those resource estimates to the production, it exceeds 8 million ounces, and several companies are very actively drilling with good results today. So here I thought it would be worthwhile visiting the magmatic tectonic setting because it's a bit unusual for Silicon, and there's a great paper out by Dave John and Chris Henry in the current GSN 2020 Symposium volume, detailing and providing a little bit more detail on the various magmatic tectonic settings of Cenozoic epithermal precious metal deposits in the Great Basin. They've got about a half a dozen different types. You can see over here on the left, light blue in color are volcanics related to the mid-Cenozoic slab rollback and the Nimbrite flare-up with many calderas. Then in the green colors here in the upper left are volcanics associated with the ancestral Cascade Arc. And then in the northern part of the figure are in orange and pink, the bimodal basalt rhyolite suite related to the track of the Yellowstone hotspot. And then around the margins of the Great Basin is a younger magmatic tectonic suite of extensional bimodal volcanism. And then finally, a more spatially restricted type of volcanism that they are calling slab window volcanism, basically volcanism that post-dates subduction in any given place and kind of trails behind and chases the tail of the retreating ancestral Cascade Arc as you move northward, as the Mendocino Triple Junction moves northward and subduction ceases. It's interesting because there's a big caldera cluster here in the area where the Silicon Project is in the southwestern Nevada volcanic field, the very south end of a large cluster of mid-Cenozoic calderas in Nevada, but it's a little bit different type of volcanism as they're documenting. And with the distribution heading up along within the Walker Lane and the number of precious metal deposits associated with this type of volcanism, including the Bullfrog and Bear Mountain District, Silver Peak, Eastside, the Patterson District, and Zaca, further in California. And so the largest example, most extensive example of this type of volcanism is this caldera cluster where we're going to be looking at today. And here's a closer view of the boundary of the southwestern Nevada volcanic fields shown in red. You can see it overlaps the Goldfield high sulfidation system. Actually, Goldfield is older, maybe on the order of 20 million years, related to the ancestral Cascade Arc. It's not directly related to this younger volcanism we're showing here. And there's shown with blue outlines are the boundaries of a series of calderas. Their ages are indicated in blue, with the youngest ones trailing off to the northwest, as one might expect. And then the cluster of known gold deposits are marginal to this main caldera cluster. Interesting, we can see that in this gray outline is the boundary of the Nevada test site. It's been around for about 80 years and has prevented modern exploration from taking place in the better part of this volcanic field, with many discoveries of gold mineralization now taking place in the only portion of this caldera cluster that's outside the Nevada test site at over 8 million ounces of production and resources and growing. It leaves the question as to how well endowed this volcanic complex really is. And it's looking like it's turning into a pretty serious mineralization area. And that's even without some of the more recent reported, nothing's been reported from Silicon yet, and some good recent drilling, the drilling's ahead by a year or two ahead of the resource estimates, of course. So if we were actually to visit Beatty as part of this talk, this little town that's right in between the Bullfrog District to the west and the Bear Mountain District to the east, we would see very dry desert hills. Not surprising, of course, because it's a very arid climate, but it's particularly dry even for Nevada because the rain shadow related to the Sierra Nevadas is very well developed. The highest peak in the Sierra Nevadas is Mount Whitney, located right over here to the left, 14,495 feet. And so it is very dry. In fact, Death Valley is less than 20 kilometers away from Beatty in a southwest direction, just over some low hills. And also, if we were to visit Beatty in the middle of the summertime, we might be surprised at how many tourists are milling around, because it turns out that Death Valley is actually a very popular place for some people to visit who want to experience extreme climatic conditions, kind of like the inverse of going to Antarctica. And ironically, just earlier this month, what may be the best documented highest land surface temperature was measured at the Furnace Creek Visitor Center at 130 degrees Fahrenheit, or a little over 54 degrees centigrade. And of course, Death Valley has the lowest elevation point in North America, located at Badwater. Another feature of interest not far from Beatty, about 40 miles to the east, are some features that kind of look like craters of the moon, which might be able to compete with Craters of the Moon National Monument in Idaho, except that visitations are strongly discouraged in the Nevada test site. That there are over 1,000 thermonuclear testing events that have been taking place in some of these valleys for the purpose of national defense. And then another site of interest is Yucca Mountain, shown right here. And that's located only 14 miles southeast of Silicon. Of course, this is the site of the proposed Yucca Mountain Nuclear Waste Repository. It's on hold right now, as you know, but its existence so close to Silicon has played a role in delaying the amount of exploration that's taken place in this area, as we'll see later on in this talk. Here's an expanded view of the land status in the general Beatty area of the Bullfrog and the Bear Mountain mining districts. As I was alluding to before, and many of you know, a number of exploration companies are very active here right now. It's a real hotspot. The land position of Corvus Gold is shown in yellow. The land position of Coeur Mining is shown in blue. The land position of AngloGold Ashanti is shown in green. Kinross also has a position, as do Bullfrog Gold Corp and Waterton. And most of the gold so far from this general area has been produced from the Bullfrog proper area just west of Beatty. In this area, about 2.4 million ounces of gold were produced from 3 open pits by Barrick Gold. Excuse me. And this mineralization is classic low sulfidation style and stockworks and vein systems associated with low angle and moderate angle faulting, hosted by tuffs and volcanic rocks of the field. And these faults are part of a detachment and listric fault system. It's been fairly well documented. And Bullfrog Gold Corp has drilled here this year, and they have defined resources, remaining resources on the order of 500,000 ounces. And then further to the north in the Bullfrog district is the North Bullfrog area. As many of you know, Corvus Gold has been very active here for a number of years. Also low sulfidation, volcanic hosted mineralization, low grade disseminated zones, and also higher grade vein systems. And they put together resources totaling on the order in excess of 2 million ounces in just this area here. And then over here on the other side of Beatty to the southeast, this metamorphic core complex has exposed basement rocks that include Cambrian carbonates. And so some of the gold mineralization is hosted by sediments. And one example is the underground Sterling mine that has produced over 200,000 ounces of gold. Another example is Secret Pass. This is an open pit that produced a little over 100,000 ounces of gold. Mineralization, mostly low sulfidation, hosted by volcanic rocks and very closely associated with the Forest Bar Canyon detachment fault system. And then similarly, a little to the northeast is the Mother Lode deposit, actually on Corvus ground. You can see in yellow here. It has produced about 35,000 ounces of gold, also primarily hosted by volcanic rocks, but some of it in basement, and very closely associated with the Forest Bar Canyon fault system. And finally, we have Silicon. In contrast to the other areas I just mentioned, absolutely no gold has been produced at Silicon. What it has instead is a steam-heated alteration zone with mercury mineralization, 2 small mercury mines, and a ceramic-grade silica pit. And of course, the expectation is now to drill underneath that and find potential gold mineralization underneath there. And so it turns out that right now, a lot of exploration activity is focused in this area, and I'm going to zoom into that part of the map here. And so far, AngloGold Ashanti's drilling has been focused in the area shown by the red ellipse, trying to get underneath that steam-heated cap. Meanwhile, their friendly neighbors, Corvus and Coeur, have been drilling just south of their property boundary. First of all, in the area of the mother lode pit, Corvus has had some very good luck finding extensions to mineralization to the north and at depth. And here's a cross-section from one of their press releases this summer. They found a number of dikes in Cambrian and Paleozoic basement rocks. Here's one hole, 125 meters at 2.6 grams. They're also identifying mineralization in the overlying volcanic rocks. And here's the Fluorspar Canyon, part of the Fluorspar Canyon detachment fault complex. It's a little bit steeper dip there. And then further north, very close to the land boundary with Silicon, both Coeur and Corvus are drilling. Corvus has a hole almost 200 meters long of 0.44 grams per ton gold. Coeur has a number of very good intercepts in what they call their Seahorse zone, also right up in this area. One example of a drill intercept is 71 meters of 1.8 grams per ton. So Anglo's got an enviable position where they're evaluating gold mineralization underneath the steam cap, and meanwhile, their visitors are illustrating potential further to the south. And there is some geologic evidence of some explanation of why there might be some type of continuity involved, because you can see the Fluorspar Canyon fault in orange here. It continues to the north and has been interpreted as following right on through into the west margin of the steam-heated cap as down-thrown rocks to the northwest. The Bear Mountain Fault bounds the range front of the Bear Mountains. On its east side, rocks are down-thrown to the east, so in its essence, there's an expected course of basement rocks that could project into the steam-heated zone of Silicon, and some regional gravity data are broadly consistent with that possible interpretation. Here's just a photograph showing the same area, but it's looking south from the Silicon area across to Bear Mountain and the basement rocks exposed in the distance. And so one of Anglo's southernmost holes drilled to date is shown here. It's an additional 1.5 kilometers to their southern boundary. Off in the distance, you can see the mother lode pit. Corvus has identified additional resources on the north end of that in the what they call the CIZ zone. It's another 2.5 kilometers north to the land boundary. And then here we have both Corvus Gold and Coeur Mining drilling with some of the intercepts that I just mentioned. So it looks like there's a lot of ground out there and a lot of progress is being made relatively quickly. But the Bear Mountain District wasn't so active 6 years ago. And 6 years ago, Renaissance was in the process. They have a modus operandi of conducting greenfields exploration to try to find additional gold properties without underlying interests. And so it's kind of challenging to fund greenfields exploration without having some nice gold assays in hand to go to investors with. And it was especially difficult back in 2014 when there was a pretty good downturn in the industry. So finally, we found a way to fund some of this sort of wildcatting work with a modern version, what could be called a modern version of grub staking. So we found a group that was willing to pay for our exploration costs in exchange for a royalty on any prospects that were developed. And that funder was Callinan Royalties, which is now Altius Minerals. And they recognized the value of conducting Nevada greenfields exploration back in 2014. So a regional portion of Nevada was selected within which to explore. Ironically, the area that we ended up selecting just barely included what would become the Silicon property by just a few miles. And then we designed within that a spatially systematic, data-driven exploration program. You know, a number of companies do this. but we compiled all types of data. We had some very large databases, combined them together in a geographic information system, geology, geophysics, geochemistry, but also land and permitting and environmental considerations to identify all open areas that were stakeable and potentially developable. And then we went about methodically checking them all out. And the first thing that brought us to Silicon, maybe not too surprisingly, was remote sensing imagery. And in this case, it was actually just Landsat imagery because steam heated alteration can have a pretty large footprint sometimes. And Renaissance uses a variety of remotely sensed imagery for exploration, including not just Landsat, but also ASTER and hyperspectral imagery. In this case, we use directed principal components to enhance an argillic alteration signature. And you can see that the overall footprint defined in the Landsat image with warmer colors indicating stronger clay alteration corresponds very nicely with some of the mineral polygons of advanced argillic alteration shown on the right that we mapped out using over 500 samples with an infrared spectrometer. So with that in hand, we also had a geologist, Lindsay, on our team who had actually been to the Silicon area, and he knew there was mercury mineralization there. Actually, the Silicon region, the Thompson and Silicon mines had a bit of a reputation as being a barren steam-heated cap with mercury mineralization and no gold. But we went to check it out. Indeed, we found large areas of pervasive kaolinite and alunite alteration. Fairly quickly on, we recognized the possible groundwater table silica zone of chalcedonic silica up to 750 meters wide. And then the other thing we noticed is that in some places, the advanced argillic alteration was so intense that even alunite, neither alunite nor kaolinite were stable. And the largest such zone is just on the other side of this ridge, Tram Ridge. So the next picture I'm going to show is looking back at the other side. This is the north side of that ridge, and there's a pit here that is basically, maybe originally they produced some mercury there because we found remnants of a small mercury retort at the base of the hill, but primarily this was a ceramic silica mine. The silica concentrations ranged reportedly from 99.7 to 99.8% SiO2. It's used, so it was mined for industrial purposes. You can see it's surrounded by a zone of strong alunite alteration. And our interpretation then, it's just the fluids were so acidic that not even alunite was stable. So very intense alteration. The other thing that's interesting to note is that there had never been a road built to this mine. There's just a little wagon road going up there, and because it's so steep and rugged, the miners found it more efficient to transport the ore to the base of the hill using an aerial tramway. You might be able to see a tram tower in the shadows here. The loading station is up at the top, and then the unloading station is down here at the bottom. And this is of significance also potentially for the district, is because this is the area, the surrounding area here is it's very intensely altered, but had never seen a drill hole by the time Renaissance arrived. And we think probably maybe one good reason is because there had never been the road building costs were too high. So here's a close-up of the Silicon pit. There are little rails coming out at the base. Here's the side of the pit. You can see a very bright white colored material. It looks like it ought to have a lot of clay or alunite in it, but spectroscopic analysis finds no evidence of clays or alunite and just a silica signature. Here's the back side of the Silicon mine facing south, a lot of open spaces, and with their little mercury stopes in here. And then in areas of stronger alteration along faults in several places away from the Silicon mine, up to several kilometers away, alteration was also intense enough to only leave this powdery silica behind. We also, when we were in the field with our initial visits, we found a lot of silicified and brecciated faults with diverse orientations, normal slips, strike slips, intermediate rakes, and complex geometries intersecting with each other. Here's an example of a structure, the main silicon mine fault zone heading south from the silicon mine. Here's an example of a step over in a silicified fault east of Cram Ridge. Wandering around here in the middle of the day in the summertime suffering from incipient heat stroke, it was easy for us geologists to imagine what these structures might look like a couple hundred meters below the surface in the boiling zone. Here's the silicon mine, or I mean the Thompson mine, mercury mine, about 1 kilometer south of the silicon mine. So a very minor mercury production, a very small remnants of a very small mercury retort were found. They had small little stopes or kind of rat holing around for mercury mineralization, and much of it in this area much of the mercury seems to have had a preference for replacing fairly coarse spherulites in the tuff. You can see an example here, and most of this mercury occurs as cinnabar and various chloride-bearing mercury species that are photosensitive and turn black on exposure to sunlight, similar to many such occurrences in the Great Basin, and also similar to those other occurrences. It's typically very finely intergrown with opaline silica. But at the very highest elevations of the property above the silicon open pit, some of the cinnabar occurs as botryoidal crusts of relatively pure cinnabar that's not photosensitive, and we've speculated that this may be evidence of direct precipitation of mercury minerals from fumarolic activities. In some places, there's not much bright red cinnabar that accompanies the chloride-sensitive species, and similar to this example from another prospect, I've seen colors like this from silicon. It's just a much lighter colored, fleshy colored, that turning black very rapidly in sunlight. This typical colors of chlorderylite, which is a mercury sulfide chloride mineral. Other minerals found in small amounts at highest elevations include small amounts of barite and crystalline quartz and possible schutite, which is a yellow mercury sulfate oxide mineral. At any rate, one of the other things we kept our eyes on was evidence of previous drilling. That's kind of the bane of wandering around in Nevada sometimes and finding what we hope is a new property, only to notice all these little piles of chips laying all over the place. And so we kept our eye out for those. We found about a dozen drill holes that had been drilled previously. We noticed that none of them were drilled in the area of the strongest alteration around the silicon mine, for possibly the reasons I mentioned earlier, because of very rugged topography and the expense of putting in drill roads. And we noticed some of the other holes were collared very close to what looked like the source fault fissure zones from which the fluids looked like they traveled and emanated, which suggested that any intercepts at depth might have crossed the associated structures at relatively shallow depth. So we thought the area was relatively lightly drill tested. Later on, we actually gained access to the assay records for most of these holes. Turns out they were drilled in the early 1990s by U.S. Nevada Gold Search Joint Venture. And they did have some encouraging results in these 4 holes right here, southeast of the silicon mine. They have an aggregate thickness of 260 feet of 0.34 ppm gold, but in widely scattered intercepts. But the best intercept was 30 feet of just under 1 gram per ton gold in hole LY008, shown here in red. That hole was lost. It was the shallowest of these holes up here. It was lost due to caving at 362 feet. It's possible that a discovery might have been made if they had been able to extend that hole to greater depths, but we don't really know for sure. At any rate, encouraged that in general the property looked relatively lightly drilled, without further ado, we staked claims, not realizing at the moment that we would be getting a lot more practice at it than we realized. And shortly after finishing our first staking job, we found ourselves crying in our beers because it turned out that a large portion of this property had been withdrawn from mineral entry because of the presence of a proposed railroad corridor for bringing nuclear waste southward to the Yucca Mountain Nuclear Waste Repository. That proposed rail line had a 1 mile total width of 1 mile buffer associated with it, and as luck would have it, the engineers weren't quite sure which way they wanted to go to get over the steep terrain around the silicon project, so they had two different proposed routes, each with their own 1 mile buffer. But it did leave an area of open ground in the middle that upon further inquiries, as Marilyn Miller investigated this, it turned out this was open for staking and there were no claims there. So it does cover maybe 30% of the steam heated zone here. So we went ahead and staked the ground, restaked the ground to optimize the location of the location monument. So that's staking job number 2. And then we considered what to do with the rest of the property, and this was back in 2014, and public sentiment regarding the Yucca Mountain Waste Repository wasn't very good. We thought it's possible that the whole thing might be dropped. The withdrawal was scheduled to expire at the end of 2015. Of course, they could have renewed the withdrawal for another 10 years, but we placed our bets, and while waiting to see if the withdrawal would expire, we prepared and submitted to the BLM a notice of intent to drill, and actually got that approved while we were waiting, so that we had some verification that we could actually proceed with the exploration within the area of the donut hole. And then, fortunately, as it turned out, the withdrawal area for the rail corridor was not renewed near the end of 2015, and in the wee hours of the following morning, we went and staked the remainder of the ground. So follow-up exploration to learn a little bit more about the silicon property and maybe define drill targets, 120 field person days, a little shy of 400 rock chip samples submitted to a full range of elemental analysis. Over 500 samples were taken for infrared spectrometry measurements, and 23 stream sediment samples were taken to try to see if gold might be leaking out in some subtle place somewhere. That didn't pan out very well. But, in any case, here's the results of the hydrothermal alteration observations. It turns out that the alunite and kaolinite distribution covers a general area of about 20 square kilometers, including the aforementioned opaline silica and powdery silica. And in this particular map, we've superimposed the alteration polygons, mineral polygons that we defined using an infrared spectrometer with a more recently acquired hyperspectral SPECTIR airborne image. And the two match very nicely. And so corroborating the efficiency of the SPECTIR to provide detailed mineral maps and verifying that our work in the field was headed in the right direction. Our rock chip geochemical sampling had more mixed results. And in terms of gold, it was actually very disappointing. Our highest verifiable gold sample was 34 parts per billion. And I'm excluding the drill chips from some of the holes that we sampled that did have reported mineralization. We got grades up to like 120 parts per billion and some of that stuff. But otherwise, in the surface outcrops, 34 ppb was our upper limit, 106 ppm arsenic and only 8 ppm antimony, looking very barren with the exception of mercury. And here are the mercury values plotted for clarity on the left. They're also plotted on the right. So the red triangles are visible occurrences of mercury minerals, and the red squares are assays of 100 ppm mercury or higher, and yellow squares are 3 ppm and higher. So very widespread mercury anomalies, strongly structurally controlled, but also disseminated. And then the structural compilation looked very interesting too. We found that these silicified structures that commonly stick up so boldly have an aggregate strike length of 23 kilometers with many complex intersections, acute intersections, obtuse intersections, stepovers, possible cymoid loops. And we didn't have quite enough detailed information to work out some kinematics of all this, but it looked like there was maybe multiple generations of movements and styles of movement on the property. Maybe with Anglo's detailed work, we could expect a lot of clarification on the structural style, and it might be very interesting. And so the most intense structure is what we've called the Silicon Mine Fault Zone, that it has a length of about 3 kilometers, extends between the Silicon Mine here and the Thompson Mine here, and then further to the southeast and the northwest. Much of the drilling to date has been focused near that key structure. Another important structure that became apparent as we did our reconnaissance work is what has been called the Owl Creek Fault Zone, shown here, kind of on the western margin of the steam-heated zone. And in contrast to the Silicon Mine Fault Zone, the fault itself in the Owl Creek Fault Zone is generally not exposed. Instead, it's marked by a very strong topographic escarpment with a significant implied offset of volcanic units, and covered up by a paleotalus or fanglomerate, basically a pile of gravel. And here's some pictures of it. When it's unaltered, it kind of looks like this up here in the upper left part of the screen, but closer to silicon, where it's been affected by hydrothermal alteration, including intense kaolinite and alunite alteration. In some places, like this lower right photo, it looks fairly loosely cemented, and it really more looks like it's just simply a pile of previously altered volcanic rock. But in other places,
well, I know that. I had no idea where you were.
Somebody's talking. So in other places, these gravels look fairly strongly indurated and cemented with silica, as shown here in the lower left and the upper right, suggesting that alteration and cementation has taken place in situ. We also thought we saw zoning relationships between the style of alteration and minerals that cut across the significant dip of this gravel package, suggesting to us that hydrothermal alteration took place while this unit had already been deposited. So a little bit of regional context is provided in this leftmost figure, where the Owl Creek Fault Zone is shown in dark blue, and it's been mapped by Friedrich and others as part of the Forest Bar Canyon Detachment Fault Zone. The dips on the Forest Bar Canyon Fault Zone and the associated Bullfrog Detachment Fault Zone, that's part of the same system further to the west. There are very shallow dips to the west, and they progressively increase in steepness to the east and to the north, to the extent that Friedrich et al. Felt, and we tend to agree, that this part of the structure is very close to the original breakaway zone at the surface, keeping in mind that it's pulling away from the core complex in the Bear Mountains down here to the south and moving off to the northwest. So here's a view of, I forgot to say something. So in where the Forest Bar Canyon fault system passes through the north part of the Bear Mountain district, it exercises a strong control on mineralization in the Secret Pass area, and likewise in the Mother Lode area. And so it wouldn't be surprising if it might be exercising a strong control on hydrothermal fluid flow and alteration and mineralization in the Silicon Mine area, which we suspect it is. And there are other indications that point to the fact that the alteration in those gravels is of similar age to the rest of the alteration, or some of the rest of the alteration at Silicon. So here's a view from some of the higher elevation portions of Silicon looking to the west. You can see the North Bullfrog area off in the distance to the right. and the northern suburbs of Beatty are just visible off in the distance to the left. And so some of the kaolinite and alunite that characterize the steam-heated zone at Silicon affecting paintbrush group tuffs are shown in the foreground. The approximate trace of the Owl Creek fault zone is shown here in the middle ground. There's additional kaolinite and alunite on the other side of the fault zone. And then what we believe is post-mineral, the younger Rainier Mesa tuff. It appears to be post-mineral where we've seen it in the field. And then on the other side of the Rainier Mesa tuff is a lava and dome, rhyolitic dome and flow and tuff complex that's also locally very strongly altered to alunite and kaolinite. Friedrich et al. Mapped these as pre-Rainier Mesa lavas and tuffs with a local source. Schilling, 1994 master's thesis from Colorado School of Mine, also mapped these as lavas and tuffs with a local source. He called them the Western Beatty Wash sequence. And both of those authors ascribed an age for these rhyolites as being actually younger than the Owl Creek fault zone based on field relationships, suggesting that this dome complex may be very similar in age to the alteration that has affected Silicon and the domes themselves. And so we'll and might actually, perhaps the subvolcanic equivalent of these domes, either beneath the domes or underneath Silicon itself, might have been a heat source and a source of metals for the system. Here's a little bit of a summary of the timing of mineralization in the area. It could definitely use some more age dating, but the first four lines here in black and blue print have to do with the lithology. So the paintbrush group tuffs have been dated, argon dated at 12.8 to 12.7 million years. They are believed to comprise much of the rocks that are hydrothermally altered at Silicon. Then the detachment fault at Owl Creek has many class of paintbrush group tuffs in it. And based on geologic evidence and the behavior of tuffs that are older and younger than this fault motion, Friedrich has pinned down the motion on that fault system, this particular strand of it anyway, at between 12.5 and 11.6 million years. Then the rhyolites, extrusive, intrusive rhyolites have been dated at 11.7 to 11.6 million years, argon, so just slightly younger. And then finally the Rainier Mesa tuff at 11.6 million years. So these first older three units are hydrothermally altered. The Rainier Mesa tuff appears to be unaltered based on our field observations. That suggests that the hydrothermal event is coming in right around here, somewhere in the 11.6 million year range. So there are two dates on alteration, two ionite dates. They're potassium-argon dates. But at the Silicon mine, alunite was dated at 11.6 million years. That falls right in that range, although there's a large error bar inherently associated with it. Another alunite date from the Thompson mine is a bit older. So we're not completely sure. This could mean that there's actually two different hydrothermal events in the area, because there is a 12 million year old event in the Bear Mountain district. Or maybe what we need is some better, higher resolution dating to help pin down the relationship of alteration to lithology a little bit better. And then compared to other known mineralization in the adjacent districts, the North Bullfrog area, the Yellow Jacket zone, has dates in the argon dates in the 11 million year range. The Telluride mine on North Bear Mountain, 11 and 12 million year dates, and many hydrothermal dates in the Bear Mountain area, summarized by Wilson et al., fall in the 12 million year range. And then the Bullfrog mine was documented by Tony Yang in his paper as a little bit younger. There's a younger hydrothermal event in the Bullfrog district at around 10 million years. At any rate, we, of course, tried to put this information into some exploration models. One thing seemed clear, and that was that the alteration of the surface seemed to comprise a steam-heated alteration zone. The shallow nature of this alteration was perhaps first documented by Mac Jackson in a master's thesis at UNR in 1988. And then the steam-heated character of that alteration may have first been recognized and documented by Steve Weiss in a PhD thesis also at UNR. And some of the information in the field that we found supportive of that hypothesis is the fact that all of the alunite only has N-member compositions of either potassium-rich or sodic-rich. The habit and texture of alunite is it's occurred as clear pseudo-cubic crystals in several places. That's also a common characteristic of steam-heated alunite. The presence of an apparent groundwater table silica zone is another obvious shallow indicator. Widespread opaline silica, as well as the presence of cinnabar and chloride-bearing mercury species. We think the water table may have fluctuated based on observations of some of this chalcedonic opaline silicate being very heavily corroded and eaten away. So in terms of predicting gold mineralization in the subsurface, we had several working hypotheses, and two of them are low sulfidation mineralization and carbonate-hosted mineralization, just simply based on analogies with mineralization in the adjacent districts. So here's an example, cross-section in 2014, with the high-level mercury zones giving way to a high-grade boiling zone at depth with possible spreading of disseminated mineralization along detachment-style faulting and including favorable replacements in carbonate host rocks. We expanded on that cross-section a little bit later by including the Owl Creek Fault Zone as a potentially important additional feeder zone and zone for possible mineralization at depth. And one argument for a low sulfidation model is the presence of illite found in drill chips that are gold bearing in some of the drill holes that were drilled beneath the steam into and below the steam heated zone. And eolitic alteration also occurs at lower elevations on the north side of the property. But we were not able to discount the possibility of a high sulfidation model either, because acid leach zones and barren gold zones can form above high sulfidation systems too. And dielite is a very common mineral peripheral to high sulfidation mineralization. And in fact, we saw alunite extending below the paleo groundwater table for up to 50 meters, and we kind of explained that away with a dropping water table, but maybe there's a different reason. And we haven't seen any silica sinters on the property anywhere, which would be more indicative of less acidic conditions. We made some effort to collect coexisting pyrite and alunite for stable isotope analyses to help answer some of these questions, but weren't successful in doing that. But maybe in the future we'll see much more information on that from Anglo. So here's kind of a schematic diagram of possible mineralization at Silicon. It's looking south in Google Earth on top and a cross-section here on the bottom. So to the west is towards Beatty, and here's this rhyolite dome field to the west. It could be a possible heat source, a metal source, and maybe there are other intrusions more proximal to silicon, with hydrothermal fluids then having the potential of flowing along a myriad of many structures of different orientations and reacting with carbonate rocks near the unconformity and then boiling and producing mineralization closer to the surface. The thing that's interesting to us is it's a very large steam heated cap with lots of structural control, and only a small part of it has been drill tested so far. So especially with the drill results further to the south by Core and Corvus Gold, we think the upside potential of this district is really good. In summary then, silicon has positive features: extensive steam heated zone, widespread mercury mineralization, strong structural control both at local and regional scales, possible pre-tertiary basement high and located in a productive district for alteration at about the right age. The challenges, major challenges to exploration were the rugged topography and that 12-year land withdrawal. But both of those challenges turned into exploration opportunities once they could be overcome. The other thing that we found challenging was the complete lack of surface gold anomalies. And even though the conceptual model is very straightforward, we found it very difficult to get a joint venture partner willing to invest in the property without those surface gold anomalies. And that's where one way that AngloGold Ashanti really shined is they recognized the value of this property. And not only did they recognize it, but they took it seriously enough and invested the time and resources and funds to build roads into the very difficult topographic regions to test the best parts of the property so that they could move forward. Here's a table that illustrates some of the issues with making blind discoveries. This comes from another paper by Dick Reed and Curtis Johnson and Mike Russell, also from the current GSN 2020 Symposium volume, illustrating that in the last 20 years, the preponderance of discoveries in Nevada have been concealed discoveries. So maybe silicon isn't strictly concealed since the steam-heated zone is exposed, but there isn't any gold there, which has its own challenges in terms of whether there really is any. It's kind of concealed from the aspect of gold mineralization, and maybe many of us geologists understand the importance of conceptual targets, but really hasn't caught on very well into the risk-taking investor groups, and so that's something that maybe needs to be worked on somehow, as many authors have predicted. We need that understanding developed perhaps a little bit better. At any rate, the other takeaway that we've made from silicon is that there are a lot of other large steam-heated alteration zones in the Great Basin that appear weakly drilled or undrilled, and many of them have mercury mineralization also. So here are 4 examples, and I have to admit that Orogen Royalties has 3 of these 4 properties, but there are many other properties like this in the Great Basin. We don't have the resources to control them all. So we think the opportunities for finding additional mineralization following the example of silicon are very good. And as one last slide, if we return to the Dave John and Chris Henry's recent paper and looking at the relatively spatially restricted distribution of these slab window volcanic rocks, interestingly, there's at least 3 other very substantial steam-heated alteration zones that are related to this group of volcanic rocks. So it's possible that we may be learning a lot more about the relationship of this type of volcanism to precious metal mineralization in the years to come. Okay, that's it. Hope that wasn't too long.
Thank you very much, Mark. That was a fabulous talk and very descriptive, and lots of geology and a great methodology for early stage exploration that you laid out. So I thank you very much, and I'm sure everyone's very appreciative for the dialogue that you gave, just outlining the steps and exploration and probably discovery. So thanks again, Mark. So I guess now, I think everyone can hear me okay. We should open this up to questions. And there are a couple of ways in Zoom that the audience can ask questions. One way is just to use your chat function at the bottom. Molly and I are the co-hosts, and we'll see your chat questions pop up. And if there aren't too many questions initially, we can have you go on the audio and actually deliver your question. Otherwise, if we get too many questions, I think Molly and I will take over asking your question for you. The other option for questions is to click on your participants icon at the bottom and use your raise hand icon, and that also tells Molly and I that there's a question, and we can unmute you that way. So with that, it looks like we have a couple of, well, just comments so far. Any questions for Mark on his talk? I'm sure there's a lot of curiosity on what's gone on. Jeff Chambers has a question. Let me see if I can unmute Jeff. Hold on just a second.
Jeff, you should be able to unmute yourself and go ahead. If you guys want to flip your video on to ask questions, feel free.
Okay, Jeff.
To participate.
Great.
Can you hear me?
Yes, we can hear you just fine. Go ahead.
All right. The question is, as written there, have you identified cristobalite in the friable silica zones?
Answer is no. I wouldn't be surprised, but we did not do any XRD work.
Thanks. That's enough. I appreciate it.
There's a question from James Stevens. Go ahead and unmute yourself, and you can go ahead and ask a question, James.
Hi, awesome talk, Mark. That was really great. I have two questions, and it might be a little complex, but I'll do my best to keep them brief. The first one is to geology. I mentioned that the predictions were being based on analogy to previously discovered deposits of similar type. Has silicon been looked at from a physics adopted first principles perspective, essentially to a boiled down silicon gold, or like gold deposits, boiled down to the most basic physical and chemical and geological fundamental principles, and reasoned up from there? Has that sort of thinking been applied, or would it be useful? And second, what were the key details that were communicated about silicon to Anglo Ashanti that allowed them to make the decision to invest in silicon? The geologic, how to clarify that geologic to what investors may just simply call theoretical.
Okay, well, for the first question, the models we were actually adopting with low sulfidation and high sulfidation, for example, or carbonate hosted, while they are taken from analogy in the sense that the adjacent areas had that style of mineralization, nevertheless, those models are well founded in geological and physiochemical theory, at least in terms of how it's expected that those deposits might have formed. So there's a background for explaining how low sulfidation systems can form, the boiling process that leads to loss of sulfur-bearing species and deposition of gold, and so on and so forth. And for the second question, AngloGold Ashanti, while we certainly shared all of our geological data with them, they have a very strong group of geologists, and they spent quite a bit of time in the field so that they could understand the geology for themselves and make what they felt was basically their own decision based on their evidence.
Thank you very much.
Okay, Carly Balo has a question, Mark, and I can't unmute her for some reason, but here's her question. Any geophysical anomalies in the silicon area?
There's regional gravity data that show a gravity high consistent with a horst extending into the silicon area. In terms of other geophysical anomalies, there are, Anglo has conducted a lot of detailed geophysical surveys, but we did not do much of it ourselves, so I can't really talk to that very much. We'll have to wait for their future talk, and maybe not in the future.
Okay, Mike Power I'm going to try to unmute you. Let's see if this works, and you can ask your question directly. Are you there, Mike? Okay, here's Mike's question. Were you able to use the SWIR data, absorption band centers, width, or shape to locate hotspots beneath the steam heated zone? If so, what was most useful?
We used, later on in the project, just like very recently in the last year, we acquired hyperspectral data from Spectier, and we used their mineral map. So we do employ a variety of methods of mapping out absorption features in gold exploration in Nevada. But in the particular case of silicon, our initial work was based on multispectral imagery, not hyperspectral. And so we haven't done that here. And so that's actually another part of the story, is the ability to map variations in mineral chemistry and crystallinity. So I can't speak to that with the data we have.
Other questions for Mark? Dylan Carlini has a question. What were the dips measured on the main northwest fault in the silica-rich zone?
I think they're fairly moderate to steeply dipping, anywhere from 50 to 80 degrees, I would say, and in many places very, very steep. I'd have to look at, I could answer that question more precisely if I review the data.
It's interesting, Mark, you were mentioning the Owl Creek Fault, I think it's called, and maybe the northward extension of the Fluorspar Canyon Fault.
Mm-hmm.
And maybe the Fluorspar Canyon Fault being at its breakaway point.
Mm-hmm.
Some of the images that you showed of stratigraphy, volcanic stratigraphy, lacustrine stratigraphy, seem to suggest that the beds aren't dipping that much, or the units don't have extreme dips.
Well, that, if you're talking about, can you still see my screen?
We can, yes.
Is this what you're talking about?
Well, yeah, and I think some of the other more panoramic shots too show kind of modest dips, but it could be perspective in the photograph. I don't.
Well, no, see, this is tricky. These, this is in the what we're calling the Owl Creek Fault Zone, but this is not the fault.
Yeah.
This is just gravel falling down an escarpment and covering up the scarp.
Yeah.
So
but those gravels look altered and maybe cemented?
Yes, that's exactly. So somehow these fluids, we believe anyway, we think that this induration and alteration, and even some of the zoning of the different alteration patterns on the hillside it cross-cut all this stuff, suggesting that it's been altered in place. And actually the time range of when this escarpment was believed to occur, based on the behavior of the older and younger tuffs around the escarpment, is such that it has an age that's actually older than the rhyolites, that dome complex that is also strongly altered not far away. So it's an intriguing area, and it takes some thought processes. If you have calderas in the stratovolcanoes around the arcs of the world, you get all these debris falling into the caldera, and you'll have all sorts of steam vents coming up and permeating through this stuff. It's maybe not that rare of a phenomenon.
Mm-hmm. Gene Klein is online. Hi, Gene. I don't know if you can unmute yourself. I seem not to be able to unmute you. Oh, there you are. Oh,
Am I unmuted?
Yep, you are. You're good to go.
Okay, Gene, fire away.
I was just wondering your confidence level of the underlying carbonate units that you show in your cross sections.
That is not constrained, as we don't have any, we are not aware of any of Anglo's drilling data that would say whether or not they've hit that basement rock. It's not very well constrained. So we do have confidence that there is I think there's a fairly strong suggestion that a basement high, it continues northward into the Silicon area, but exactly how deep that basement is not well constrained right now. And we were going to run a gravity survey on our own, but without drill hole constraints, the advice given to us is that even with more detailed gravity data, it would be hard to sort of quantify that depth. So we didn't do it.
Thank you, and great talk.
Thank you.
Andrew J has a question. Andrew, if you could unmute yourself. Again, I can't seem to be able to unmute. Oh, there you go.
We're unmuted for a second and we lost you. Maybe try it one more time, Andrew. There you are. Go ahead.
Great presentation, Mark. Thank you. My question is, when a project has barren steam heated alteration at surface, such as silicon, do you have any key elements that you like to use to indicate that such a barren alteration system could be hiding mineralization at depth?
Yeah, so there's various information that's come in through publications and personal reports as to the utility of some volatile elements in addition to mercury. In our case, we can't contribute anything useful in that regard, except there's even been debate as to how important mercury mineralization is in that environment. Our perspective on that is that if we don't see mercury, we don't take it too seriously as a negative factor, but if we do see mercury, we consider it is a positive factor, although I don't think there's complete agreement on that in publications around the world. But I have one slide I didn't use because of time constraints. There are a number of great examples of gold mineralization underlying mercury-rich steam-heated zones in Western North America. This would be one more example. We think, obviously they're not all going to be mineralized, but the ratio's probably not too bad. So I think mercury helps, definitely.
Okay, thanks, Mark.
Mark, I have a question, and it has to do with the depth of mineralization from the near surface environment at Silicon. And if you head southward along the Fluorspar Canyon fault system, you get into these Carlin-esque deposits at Secret Canyon and Mother Lode like you describe. Is there a way that, or maybe you guys have speculated on the depth that those deposits form? Maybe have reconstructed in cross sections the depth of those deposits versus what you see at Silicon to the north?
I guess I'd say I don't think we've really tried to track that groundwater table, if you will, across, but I would say that there is quite a bit of steam-heated alteration down there. It gets much closer to the basement rocks down there than it would be at Silicon. So there's, how much different the paleo groundwater table was down there versus Silicon is not very clear to me, but clearly gold mineralization is a lot closer to the surface. And but the lithologies are changing. Those carbonate rocks are a lot deeper at Silicon. So there's got to be there are some differences because there has to be, because the gold is, in some places it's not, but there's a lot of structural dynamics going on there. So we haven't tried to unravel that.
Yeah, there's quite a bit of post-mineral
Right.
movement on the Fluorspar Canyon fault. Okay, Jason Craig, let me find you on the list. You've maxed us out with people here, so I have to find everybody on the list.
He's unmuted. You should be good, Jason.
Okay, go ahead, Jason. Ask your question.
Hey, Mark.
Hello, Jason.
Thank you. Awesome talk. And I just wanted to ask, I think you mentioned that you didn't have much control on the kinematics of the faults in the area, but I was wondering if you could just kind of elaborate as to why you think alteration is primarily distributed on Northwest Striking Fault, what you think could be the kinematics of faults in the area, and then the specific structural setting controlling the localized fluid flow that you see, the highest precious metal values in.
Well, some of the strongest alteration occurs along the northwest striking Silicon Mine fault zone, and it's a lot of alteration on a number of faults of different orientations. I don't think we've really worked out some of those dynamics. I have seen strike slip Walker Lane oriented strike slip faulting cutting across older, more normal dipping faults to suggest that there's maybe some evolution in the tectonics with time. There may be more than one stress regime involved. Maybe some of it's post-mineral, but we also don't know what's happening in the subsurface. We can only see what's at the surface, and fluids tend to spread out more near the surface. So, those are some questions that we'll probably be seeing some more answers to when Anglo starts talking about their data.
Great, thank you.
Chuck, yes, we can hear you, but you gotta talk louder for once.
Oh, sorry about that. Mark, have you given any thought to redoing the argon, the KAR ages of Ted McKee to argon to better correlate with between the mineralization and the age of the units?
I think that would be a great thing to do. And
Mark, can you repeat the question so everyone can hear?
okay, I think what he's asking is suggesting that it would be useful to get higher resolution radiometric dating on the alteration itself. Is that correct?
Yes.
Yeah, so I think that would be a great thing to do. It's out of our hands now, and that's something for AngloGold Ashanti to consider. Especially if there's more than one age of alteration, and especially even more so if there's more than one period of kinematic style of motion.
Well, they overlap, and KAR wasn't so great 30 years ago.
Right. Yeah. Well, yeah. So that was 1993 when those KAR dates were done. So that's 27 years ago.
Mark, it's interesting, a lot of the volcanic stratigraphy was done on behalf of the Yucca Mountain Project and DOE funded studies by Chris Friedrich and others in the late 80s and early 90s, mid 90s maybe. How valuable do you think their work was in sort of understanding the overall caldera geology and the geology of the Southwest Nevada volcanic field in general? And how has it helped you guys?
Well, it was extremely helpful for being able to put the features observed at Silicon into a regional context that helps unravel the timing and sequence of mineralization in the area. So, there's Tony Yang's work, there's Steve Weiss, and there's, yes, and the USGS Friedrich, and nobody's perfect, and actually the caldera boundaries are evolving with time, but there's very interesting stories of putting together. If you look at the descriptions of the detachment faults in each of these different little areas and see how they fit together, it's a extension. Maybe that perhaps one reason why this area might end up being so very nicely endowed with gold mineralization is that the intensity of extensional processes related to this detachment fault system that were just popping off at the same time as the calderas were going off. But yeah, so I mean, these other works are very, very helpful.
Don Ernest has a question. Don, can you go ahead and give your question?
Yeah, I spent 8 years working in the general area, up around Silver Peak Caldera with Sunshine Mining. And then we had a large block of ground north of Beatty, around 86, 87. Anyhow, this is a great talk, but it sure looks to me like silicon might be perched right at the intersection of a caldera margin or a ring fracture and a radial fracture, which would be that Owl Creek fault. You know, it's just a simplistic overhead look at that, but you know, there's a lot of calderas in that general area of Nevada, and you know, that may be where this thing sits.
Well, that is correct. It's the Owl Creek fault zone comes in at nearly right angles to the Rainier Mesa caldera and the Ammonia Tanks caldera, and as such would be coincident with a radial tension fracture coming out from that caldera. So you got some sympathetic motion associated with caldera disruption versus extension related to the detachment fault system.
Any other questions? Okay. Well, fantastic. I had a lot of fun tonight and I learned lots. So thanks, Mark. I'm sure others did too. And it's always nice to hear about the early stages of an exploration discovery. So with that, I guess join us maybe next month. We're trying to work out our September talk still. We certainly have an October talk, and that will be Tom Benson of Lithium Americas talking about the Thacker Pass lithium deposit over at McDermott. So we appreciate all you guys showing up. It's great support, and it's always nice to hear good geology. So thanks again, everyone.
Thank you, Mike.
Thanks, Mark.
Thanks, Mark.
Thank you.
Thanks, Mark.
Thanks, Mark. That was great.
Hey, thanks, Mark. That was great.
Thanks a lot, Mark. Nice talk.
Thank you, Buster.